Welcome back to Sustainability Ventures, where we dig beyond the headlines to uncover what really works in climate solutions. Carbon capture and storage, or CCS, is often hailed as the technology that will let us keep burning fossil fuels while still hitting net zero targets. Trillions are being invested globally into carbon capture plants, CO2 pipelines, and storage projects. But here's the critical question few people ask. Is carbon capture physically capable of doing what we hope? Today, we'll explore why carbon capture faces thermodynamic limitations and why that matters for climate policy, energy systems, and the economy. Let's break it down. First, a quick refresher. Carbon capture technology is designed to remove CO2 from power plants, industrial processes, or directly from the air. There are three main approaches: post-combustion capture, scrubbing CO2 from exhaust gases; pre-combustion capture, removing CO2 before fuel is burned; and direct air capture, pulling CO2 straight from the atmosphere. Sounds promising, right? In theory, we could stop billions of tons of CO2 from reaching the atmosphere. But here's the catch. Every step of carbon capture consumes energy, sometimes a lot more than people realize. That's where thermodynamics comes into play. Thermodynamics is the study of energy and its transformations. To capture CO2, you have to overcome the natural tendency of gases to mix. That's called entropy. In simple terms, separating CO2 from air or flue gas requires energy, lots of it. For instance, capturing 1 ton of CO2 from flue gas can consume 200 to 300 kilowatt hours of energy. Direct air capture is even worse. Removing CO2 from the atmosphere where it's only 0.04% of air can require 500 to 800 kilowatt hours per ton. This energy has to come from somewhere. If it comes from fossil fuels, you may emit a significant fraction of the CO2 you just captured. Even if renewable energy is used, it reduces the amount of green electricity available for homes, factories, and EVs. This is called the energy penalty. Here's what happens in a typical coal or gas power plant retrofitted for CCS. Plant efficiency drops by 20 to 30%. Fuel consumption increases, burning more coal, gas, or biomass. Costs per MWH of electricity rise significantly. Some estimates show electricity costs double after adding carbon capture. So while CCS reduces emissions, it comes with a hefty trade-off: more energy use, higher bills, and potentially higher life cycle CO2 emissions if fossil fuels are involved. Carbon capture relies on materials that bind CO2, like amines, solid sorbents, or membranes. But physics limits how much CO2 these materials can absorb per unit of energy input. Amine solutions degrade over time, losing efficiency. High temperatures or impurities can destroy capture materials. Scaling these systems to capture billions of tons per year requires unprecedented volumes of chemicals and infrastructure. Even the best materials today can only capture a fraction of emissions at realistic energy costs. Direct air capture, or DAC, pulls CO2 directly from the atmosphere. The problem? CO2 concentration is extremely low, 0.04% of air. That means capturing a single ton of CO2 requires processing over 2.5 million cubic meters of air. The fans, pumps, and heaters consume enormous energy. Thermodynamics sets a hard minimum. There's no way to capture CO2 for free. You're always fighting nature, and nature always wins some of the time. Because of these thermodynamic limits, carbon capture is expensive. Current post-combustion CCS costs $60 to $120 per ton of CO2. Direct air capture costs $250 to $600 per ton. Compare that to carbon pricing or investing in renewables, which can reduce emissions more cheaply. This raises a critical question for policymakers. Should trillions go into CCS when energy efficiency and renewable energy offer higher returns for the same emission reductions? Carbon capture is not magic. Thermodynamics is unforgiving. A green future will require smart use of CCS, but it must be paired with renewable energy, efficiency, and behavioral change. If you value science over hype, subscribe to Sustainability Ventures, share this video with someone who thinks carbon capture is a silver bullet, and help spread the word that the energy transition must respect the laws of physics.